Good morning and welcome to the ALCF developer sessions of July 2020. My name is Yasaman Qadar and I'm a part of the training team at ALCF and also a member of performance engineering team. These webinar series are created to foster discussion between the early developers of the softwares and the users. Today's topic is best practices for queuing and running jobs on Theta. We have three presenters today. They're all from Oregon National Laboratory. I believe the order is Adrian Pope. He's an assistant computational scientist. He's working at the intersection of data, computing, and statistical methods for cosmological interface. Chris Knight, he's a Catalyst team lead. His research interest includes advancement of molecular simulations to model soft condensed matter, using both classical and initio methods and understanding scientific application performance and future computational resources. And Misha Salim, he's also an assistant computational scientist. His research interest includes data science and Balsam workflow management. Thank you all for being here today. Adrian, please take it away.
Okay, thanks a lot. So I'm Adrian Pope. A quick outline, there's sort of three sections of this talk. I'll be presenting the first on sort of scheduling policies in Cobalt, our scheduling software. Then Chris will present a middle section on tips for short and interactive jobs. And then Misha will do the last section on workflows and ensembles, sort of more tips on how to pack multiple jobs together. And mostly this is a higher level talk, meaning in a lot of cases we'll be talking about concepts and assume that users have some familiarity with our systems and the commands on the systems. When you get the slides after the presentation, there will be links in them to parts of our documentation. So if you need to look up specific syntax, you can follow the links. We'll point out syntax in cases where it's proved to be either not obvious or tricky. So the first section's scheduling policies in Cobalt. And we wanted to start with a cartoon overview just to get everybody on the same footing of what runs where when you log on to our systems, especially the Theta system, and run jobs on the compute node. So Theta is actually composed of three sets of nodes. They're the Theta login nodes, the Theta mom nodes, and the actual compute nodes, which are labeled by this node ID and then a number. So when you SSH to Theta, you end up in a shell that's running on the login node. Then when you actually start to run a job, you write a job script and you put that in the queue with the qsub command. And anything that's in that qsub script is actually going to run on the Theta mom node. So if you say qsub, it'll go into the queue. When the script actually launches, it gets opened up into some shell on the Theta mom node. And so you're executing this script on these Theta mom nodes, which are sort of like controller nodes. But architecturally, they resemble the login nodes, not the compute nodes. And as the Theta mom node is going through the script, it'll hit something like app run. And this is the actual command that launches an executable onto the compute node. It's the app run statement that actually launches a job onto the compute nodes. And so what we're going to talk about later, it's sometimes helpful to remember what is running where. And so when we talk about submitting and running jobs at a high level, we're mostly talking about two different tools. So one is Cobalt, and that's software maintained by ALCF. And this is the software that manages the job queue. It decides what job is going to run on which nodes and when. And interacting with this, a user usually writes a job script, submits that script to the queue, and as we saw, that script eventually runs on a Theta mom node. And commands for Cobalt, a lot of the things that start with Q are Cobalt commands. So qsub for submit, qstat to see what's going on, qdelete, qalter, qhold, qrelease. And then when we looked at that cartoon with the script, there was the app run command, and that's part of ALPS, which is a Cray product. And this is, a command that's in your job script. This is what actually launches everything onto the compute nodes. This is the command that handles things like MPI details and processor affinity and all the stuff you need to know, the details about when you're going to launch on the compute nodes. And so we're not going to go over syntax for most of this. So when you get the slides, you can follow the links to look at all the syntax. But to see a quick example of what sort of this looks like in code space, So your executable, whatever program you want to run on the compute nodes, is invoked within a script, something like a bash script or a C shell script. I tend to use bash, but I think you can use whichever. And apron is that alps command from Cray that launches the executable. So here we have an example. So cat myscript, say you wrote something called myscript. At the top it shows what shell it's using. These special hashtag Cobalt commands pass parameters to the scheduler. Then there's just an echo statement. It's a shell script. You can do things like echo. And then there's the apron command. And this is where you get all of the, the MPI details, the total ranks, the ranks per node, the affinity, things like that. And then if you actually want to submit this to the queue, you do qsub the script, qsub myscript.sh, and it'll give you back a job ID, which you can use to track what's going on. So again, if you want to look up the specific syntax for any of these things, follow the links. We did want to take a minute and just note a few of the qsub attributes that you may not use all the time, but are useful to know about occasionally. The first one is how to set memory modes, and there's a lot more documentation on our website about the memory modes for the compute nodes, but you can sort of reorganize how the NUMA memory modes go to the different processors. And so with qsub, you'd put this -- adders and then mcdram and NUMA to tell it what kind of mode to run things in. There's also using the high bandwidth memory either as a cache or as its own separate memory space. There's a not often used attribute called location, and this is used by people usually doing performance studies if you want to make sure that your job is always running on exactly the same nodes, because there is node-to-node variation and there is slightly different network connectivity between different sets of nodes. You can actually tell Cobalt the exact list of nodes that you want to use, and it will wait and run your job on those specific nodes. So that's good for some sort of performance repeatability measurements. Each node also has a local SSD, and to be able to use that from your job, you need to pass this -- adders SSD, S required, and then the size. I think you also have to email support and have your account enabled in order to access that. And finally, especially when we get to talking about the interactive sessions, by default, you will not be able to SSH to the compute nodes, because we saw, if your job script, the script part will run on a Theta Mom node. If you open an interactive session, your shell will be running at first on the Mom node. If you actually want to be able to SSH into the compute node, you have to also include this -- adders enable _ SSH = 1. And if you do that, then in an interactive session, you could SSH to the compute node itself. And if you're in a script, you could also go to a Mom node and then go to a compute node. And so here we also you'll have an environment variable called Cobalt part name that will be in the shell that's running the job that'll show you which nodes your job is running on. And then to actually create the node ID name for the compute node, it's NID, and then enough numbers to span 5 digit spaces, 0 padded. So in the bottom, you can see the example for the first node would be NID, and then 4 zeros and a 1. So these are useful to know about for certain specific cases. And then sort of a reminder, once your job is queued, you want to keep track of what's going on with it. If you're on the command line, you can use the qstat command to get a list of your jobs or all the jobs in the system. It has a lot of different header possibilities. I highly recommend reading the manual page and setting the header to what columns you want to see. I think the default columns can be a bit verbose. There's also an environment variable you can set with your default preferences. A somewhat more graphical user interface way of looking at what's running is the status web page, which we also call the gronkulator for reasons I don't actually know. But this is a page where you can get a graphical representation of what jobs are running where. You can see what's running, you can see jobs that are starting, you can see what's queued, and you can see any reservations that are in place. And so it'll show you not only active reservations, but future planned reservations. We'll talk a little bit more about those later. Okay, so Theta's queues. So when you write a job script for what you want to run, then you have to submit it to a queue. And there are basically only 4 queues on Theta. There are 2 debug queues. Each of them are 16 nodes. One is in cache mode for the fast memory. The other is in flat mode for the fast memory. And these are just for small, short debugging jobs. Default is the main production queue, and we'll spend most of the rest of the talk on that. So we'll get to that in the next slide. There's also this queue called backfill, which I think is useful just to know about. And so unexpired projects that have used all their allocation but haven't formally expired, they can still submit jobs. And those jobs will have access to the same nodes as default, but backfill jobs are always lower priority than default jobs. So basically a backfill job will only run when there's a window in between the other jobs that no default job can use. But this does happen. And my sort of anecdotal advice is that shorter jobs generally have a better chance of running through backfill. But for this talk, let's focus on the default production queue. All right, so just a quick rundown of like what the sort of policies are for that queue. Any user can queue 20 jobs. They can have up to 10 running at a time. You have to request at least 30 minutes, and that has to do with how long it can sometimes take to start up a job on the compute nodes. And then the smallest partition you can ask for in the default queue is 128 nodes. And then as you request larger and larger node counts, you get access to longer and longer wall clocks. So this is one way we encourage users to try to run very big jobs. So we're a leadership compute facility, and our charge is really to run jobs that you can't run at other facilities. And once you get up to about 20% of the machine size, which is 802 nodes, then you access our longest wall clock, which is 24 hours. And so now I'm going to start to talk a little bit more conceptually about how the scheduler works and how you may want to use that to try to get the jobs for your project to run efficiently. So some key concepts. So a queue, after your job is submitted, it enters one of these queues and it waits to use the system. And Cobalt, as we said before, is the software that manages the queue and determines what will run where and when. And Cobalt organizes the queue through what we call a score. So as jobs are ordered in the queue by the score they have accrued from greatest to least. So the job that has the highest score will be at the top of the queue. It will be the thing that Cobalt is looking to put on the machine next, trying to create room for it. And so, we get asked a lot, especially lately with deep queues, like how long is my job going to wait? And this is actually a rather complicated question. And so we don't have really succinct guidelines on how to do this. But I would say that at a broad level, I think about dividing this into 2 factors. And one of those factors is the rate at which your job accrues score according to the score function. We're going to talk more about that later. So some jobs will accrue score faster than others. So that's one thing that determines your wait time. But a subtler thing is the score required for a particular job size and length to run given the current queue conditions. And this is the part that is pretty tricky to judge. For very large jobs, it's intuitive and it looks to be true that they usually have to wait to get pretty near the top of the queue to run. So, obviously if you have a full system job, you need to wait until you're the highest priority item before the machine is going to put your job, before Cobalt will put your job on the machine. But even if you're not full system, you still generally have to wait for a large part of them. You basically have to wait for Cobalt to very intentionally put your job, make room for your job and put it on the machine. At the opposite end, if you have a really small, really short job, we talked about this a little bit with the backfill, sometimes there are windows. So if Cobalt is trying to clear out space for a really big job, after a number of smaller jobs have been running, there will usually be these little pockets where, a job finishes and there's, a half hour or an hour of space before the big job is going to start. And so Cobalt will look for small short jobs that it can plug in there to use the system efficiently while it's draining. We call this draining for a bigger job. So it turns out that small short jobs can actually have much less queue latency than you would expect. So they don't need to make it to the top of the queue. So it's not as important what rate those jobs accrue score. What's important is how quickly they can fit on the machine. But in general, the deeper the queues are, the larger the scores that are going to be required for any of these jobs to get on the machine. So all types of jobs tend to see longer wait times when the queue gets very deep. So I wanted to talk a little bit about the score function so that you know how to look at the queue and how to understand how your job is moving through the queue. So all jobs have the same initial score, and this is there's not any particular deep meaning to the score scales, but they all start at a score of 51. So anytime you submit a job, it's going to start with a score of 51. And what's important is the functional form. All the jobs have the same functional dependence on time. So all the jobs will grow in time on the same function. And that function is super linear. And by this, I mean the time derivative starts very small and increases later. And so what this looks like is jobs initially gain score very slowly, but they'll build up steam later. So you'll submit your job, it has a score of 51, and initially it doesn't look like it's moving anywhere. And that's because of the super linear functional. So it will start moving up later. How quickly it moves up depends on the job parameters. So in front of this functional dependence on time, you have a coefficient. And that coefficient is dependent on a number of job parameters. And again, just to go over this again, jobs with larger coefficients, they'll still start at the same initial value, but the advantage of having a larger coefficient is that you'll rise faster and you can pass other jobs that were submitted before, and you'll get to the top of the queue more quickly. So the three things to be most aware of in terms of the coefficient is first is the project type. So if you're an Insight or an ALCC project, that will accrue score more quickly than a director's discretionary project. Another important factor is the number of nodes. So the more nodes you are running on, the more quickly you'll gain score. And this is another thing that we do to encourage leadership computing, to encourage running the jobs that are too big to run on anybody else's systems. And wall clock. The shorter your job, you'll accrue score more quickly. And this is to encourage users to accurately estimate job time. So not to say, oh, just give me 24 hours and my job will finish sometime in there. And what this helps from the scheduling side is the more accurately that we know how long a job will run, the more efficiently we can schedule things on the machine. An important thing to know is that when jobs are on hold, then the score and the rate of change of score will hold steady. You won't be increasing score or increasing the derivative while you're on either a user hold, a dependence hold, or an admin hold. So this means that score and the time derivative are functions of what I call eligible wait time, which is the total time you've been queued minus the time you've been on hold. This can get a little confusing because of all of our tools like qstat. In the status web page will show you queued time. And so this can be a little confusing for jobs that have been on hold. You'll see some jobs that look like they've been queued forever and haven't accrued much score yet. But if they've been on hold for a long time, that can explain it. So the age of deep queues. So Theta's queues have been historically deep by our standards since about May of this year. And by deep, I mean typically 5 to 10 times deeper than they were in 2019. So across the board, we're seeing projects wait, up to 5 or even 10 times longer than they were used to waiting last year. So it's become more important to sort of learn how to estimate how long your jobs might wait to run. And so what I do to sort of get a feel for what's happening on the machine right now, I look at, qstat or the status web page, and I sort of look at jobs in different score ranges and see how big and how long they are and how long they've been queued to try to get an idea. Okay, if I ran a job of this size and this length, how long would it take to get near the top of the queue? And as a side note, my personal estimate for the wait time difference between a director's discretionary job and an Insight or ALCC is about a factor of 2. So if you submitted the same job from Insight ALCC, it would wait about half the time that a director's discretionary job would wait in order to get on the machine. So as I said before, optimizing the overall project throughput is subject to the constraints of the project, and it's a hard problem to state a general solution to. As I said, large jobs accrue score more quickly. When they run, you can use a whole lot of core hours. Very small jobs, they can have lower latency when they can find windows, but they're short wall clocks and not using many core hours. And the middle ground and crossovers are sometimes pretty hard to figure out. Like, I sort of generically say large and small jobs. I don't know exactly where the crossover is. Anecdotally, I think 128 and 256 node jobs get through pretty quickly. It seems that those are easier to find windows than sort of 500 or 1,000 node jobs. And so a lot of the rest of the talk will talk about organization tools to help you, we want to do a reminder of what tools are around to help you organize your jobs to try to take advantage of getting through the queue as efficiently as you can or for your project. For help and advice, Insight and ADSB projects should have catalysts, and ALCC and DD projects hopefully have some sort of ALCF contact. If you get stuck, you can always email support. So I'm going to talk about ensembles a little bit. And so the idea here is that you can gain efficiency by packing jobs together and waiting in the queue once instead of separately for each job. And if you have a really simple set of jobs, you can do this in what we call an ensemble Cobalt script. And I would say generally classify these into 2 types. There's serial. So in a serial ensemble, you have a number of jobs that are, basically the same size, but are short compared to the wall clock limit. So you want to run a sequence of app runs in a script. And then there's the parallel case where you have a number of independent jobs that are similar in time length, and you want to run multiple app runs at the same time. And an additional benefit of this is if you bundle small jobs together into a larger job, sometimes you get access to longer wall clock limit. And then when we're thinking about complexity, you can mix parallel and serial in the same script. It's just a shell script. But at some point, if you get complicated mixes of sizes and lengths and dependencies, you might want to consider a workflow tool, which we'll get to later. So a very simple example of a serial ensemble. This is a pretty straightforward shell script. You just basically have app run commands after each other on successive lines in the script. And in this case, a later app run call can depend on the output of the previous. We know what order they're going to run in. Parallel ensembles are a little bit more complicated, so I wanted to take a little more time on this. But basically, now each app run has to be backgrounded so that we can start other app runs before the first return. So after the app run command, we have this ampersand to background it. This sleep 1 in between the app run calls is important. This is what allows the resource manager to get a second to breathe, make sure it knows which nodes have been allocated to that app run so that it knows when you call the next app run to go fill that from a set of empty nodes within your job. So that sleep is really important. And then after the last app run, so we've backgrounded all these app runs, but we don't want the script to exit because that'll take the job down. So we have to have this wait at the end. So that's just like a bash shell command to wait for all the backgrounded tasks to finish. Then the script can exit, and then the job can be done. There is a limitation here that you can have no more than 1,000 app runs at a time in any job. And I would say if you need more, then you should be looking into a workflow. So job dependencies are another tool that we have for organizing jobs. The case here is when we want to run a sequence of jobs in a particular order. So a common example of this is a very long simulation that requires more wall clock than you can get with a single job. And if your code employs a checkpoint restart mechanism, you can run part of the simulation, stop, and then restart from where you left off. And so to help with cases like this, Cobalt has a concept of dependencies between jobs. So this is a way of saying, don't start this next job until the one that it depends on has finished. So this mechanism guarantees an order of jobs and that only one job will run at a time. And an additional benefit that is perhaps not well documented is if you have a chain of dependent jobs, the subsequent jobs will inherit some fraction of score that the previous job had to build up by the time it ran. So the idea here is that it should decrease your queue wait time in between jobs after you've waited for the first one. I think knowing some details of this process can help with the user experience. So just to do a sort of detailed step-by-step walkthrough, job one, you submit, it begins accruing score, its state is queued. You submit job two with a dependency on job one, and it's put into a dependency hold state. And as we said earlier, a job in a hold state does not accrue a score or accumulate wait time. So your later jobs will just sit at the initial score value while the first job is waiting to run. So then the first job accrues enough score to run. When it finishes, the second job is released from its hold state, and at that point it inherits a fraction of the score that the first job accumulated in order to run. And the default for this, I think, is currently set to 50% on Theta. So job two is now in a queued state, and it starts accumulating eligible wait time and accruing more score on top of what it inherited from the first job. An important caveat is what can go wrong. So if the first job returns a non-zero exit code, job two, instead of going into a queued state, will go into a dependency fail state. And this is to help out with unexpected crashes. Like if the first job in a dependency chain fails for unknown reasons, you don't necessarily want to go and try to launch jobs after that. And you can release from a dep failed state into a queued state with this queue release command, but the score transfer is lost. So there are examples of how to mitigate this, and a case where you often want to mitigate is the case where your job is just interrupted by the scheduler. So your code just runs until it times out. The return code in this case is non-zero because it was interrupted by the scheduler, and this will hang up the chain and mess up the score inheritance. But if your code has a checkpoint restart mechanism, you may not care that your first job ran out of time. You'll just start from the last checkpoint no matter what. So Cobalt scripts are just shell scripts. So you can trap signals and return zero, even if you were interrupted by the scheduler. And so Ray Loy wrote this no-fail script as an example of how to do this. So in this pseudocode here, you would just copy Ray's version of no-fail to wherever directory you're running your jobs and use it to wrap your script. This is not an officially supported product, but it's been used successfully. So I encourage you, if you have a case like this, to copy that script and take a look at it. One thing to know is JavaScript's going to have these hashtag Cobalt lines. If you're wrapping your job script, this your script with no fail, any of the Cobalt lines in your script are not going to be, Cobalt is not going to see that. It'll just see hashtag Cobalt lines in the no fail script. So you can either put those values on the command line, like in here we have a dash time of 5 minutes, dash number 64, or you can edit your copy of no fail and move your hashtag Cobalt lines into that. So special cases. So occasionally projects have needs that really do fall outside of the normal queuing policies. So they fall outside of what we can do with default. So we ask these projects to fill out the form that we've linked above. It's called a reservation form. But based on that, we can decide whether to take a number of actions, and it can take several business days for us to figure out what to do, depending on how complicated the request is. So things that we can do, score boost. So say you've got an urgent deadline for a conference submission, proposal submission, a journal paper, something like that are highly urgent, and it doesn't look like a job is going to run in time. We can boost the score of a few jobs to meet those requirements. We have what are called reservations. That's where a set of nodes can be reserved in advance for a particular time. And this requires stronger justification than a score boost because it's pretty disruptive to scheduling. So that requires stronger justification. And then the usual most extreme example is if a project really needs to regularly run something that the default queue just doesn't support, we can set up limited access special queues. This is a really rarely used device, and it requires extremely strong justification, and we usually get approval from very high levels of ALCF management. And I thought it would be useful to know, especially now, how to judge the maximum job size that you can run on Theta at any time. And so normally Theta has 4,360 nodes available to the default queue. Rarely a node will not show up after maintenance. This is an not common case, but it's relatively easy to check for. You use this nodelist command, you look for all the default nodes, and then you just count the number of lines. And this is normally 4,360. A node can also be recognized by the system but down, meaning it's had some sort of hardware problem and is essentially visible but offline. And so this, I do nodelist to look for default, look for the nodes that are marked down, and count the number. And this I'll subtract from however many nodes are available. We also have reservations on the system for things like, right now there's a high performance computing school going, and they reserve some number of nodes during the day for the students. So you can use the reservations tab on the web page or show res to see what's there. It's a little hard to tell the number of nodes that are in a reservation, so I have just here a quick example of how you could copy and paste a list of node ranges from show res or the reservations tab and put them into a command line utility and count the number of nodes. So that's another way I can figure out how many nodes to subtract from 4,360. And for the last several months, COVID-19 research has had a standing reservation of 260 nodes. And so the baseline for largest number of jobs in the last few months has been, our largest job size is 4,100 nodes minus however many nodes are down. And it's important to note that Cobalt at all times will allow users to queue jobs up to 4,360 nodes. But if there aren't enough nodes available, the job could get to the top of the queue and just sit there because there's not enough resources available. So it is important if you're aiming at really big jobs to know how to tell how many nodes are actually available. And then just a quick, other policies from ALCF that are relevant to project planning. The most important one, I think, is overburn for Insight and ALCC. So this is a policy where projects that are Insight or ALCC can use up to 125% of their allocation for capability scale jobs, so these jobs that are larger than 20% of the system. So that's a sort of a 25% bonus. Smaller jobs will still go to backfill when a project reaches 100%. All jobs in that project will go to backfill when a project reaches 125%. This is available for the first 11 months of an allocation year. So for Insight, that's beginning of January to end of November. And for ALCC, that's the beginning of July to the end of May.
My name's Chris Knight, as Yazi introduced earlier. And I'll cover a handful of slides, more focused towards short and interactive jobs for those types of workloads where you really want quicker turnaround time on the smaller scale. A couple of general hints, though, that are applicable to short, long, small, large jobs. It's always good to check your quota every once in a while. This may be more particularly relevant for the DD projects that have relatively smaller file system quotas. Maybe you're doing some debugging work and generating a lot of core files. You'd want to make sure that you have enough space available to do that work instead of waiting to find out after a job actually runs that you ran out of space. Also, checking to make sure that you have enough core hours available to run those jobs. This can be particularly helpful if you come into the office at the beginning of the week and you plan on debugging something intensively, only to find out you don't have the hours you need to do that debugging work. So these are good things to query every once in a while. So to understand how to get jobs through the queue quicker, it's helpful to understand the aspects of the queuing system that might be holding up your job. One possibility, and that's going on this week, as Adrian mentioned, is that there may be reservations in place on some of the nodes throughout the system. So although it may look like there are idle nodes in the gronculator, they're actually reserved for some special use case. And so in addition to looking at the reservations on the gronculator, you can use the show res command to see if there's anything currently active on the system. It may be that what may look like idle nodes they're actually in a starting state, or they're in a cleanup state, or maybe they're down. And so there are a number of reasons why nodes that are not currently running a job may not be at this time available to start a job. To check some of the status, you can use qstat. And then I'll spend a little more time on the nodelist command. But again, also the gronculator can help with understanding what's currently on the system. And by looking at the queue and what's Cobalt will be trying to schedule next, try to get a sense of what might be able to run throughout the day. In the context of the reservations, I would pay particular attention to the ALCF weekly updates for any training announcements and the associated reservations, and in particular maintenance notices. I'll say a little bit about this in the next few slides. But now turning attention to nodelist. Nodelist is a particularly helpful command, giving a good idea of what the current state of the system is and what might be available to run jobs on. Another important question is to consider is, trying to understand when a job might start. Every user asks this question, after a job is submitted. It's difficult to answer, as highlighted by some of the points that Adrian made earlier. It really is, it depends on the dynamic state of the queue. There is one estimate that is available to users if you'd like to look at it. It's one of the headings for the qstat command, the estimated start time. And this is, I'll call it a pessimistic estimate, but it's a very simple calculation of all of the machine hours that are queued ahead of your job divided by the number of days to give you an estimate of when your job might start if everything went through the queue as is. More often the case, if you periodically check the estimated start time for your job, it will decrease faster than linear over time as things in the queue change. Jobs finish early, jobs fail for one reason or another, or according to the relative score accrual rates, jobs may jump up and down in front of other jobs. So I would use this just as a rough estimate for some of the bigger jobs, if you're interested. Now, for short test jobs, and I use the word test, but there may be a reason for short production jobs. But there's a number of reasons why short jobs are useful. Maybe you're debugging an important issue in your code and it only occurs at scale or a modest or reasonable scale. And you really want to be able to have the ability to run multiple tests without dealing with the latency of sitting in the queue to resubmit a job. And so within a single job, you want to be able to run multiple tests repeatedly. Whether these are testing the results of optimizations and profiling, or testing a new capability, or trying to test a fix to the issue that you're debugging. As Adrian pointed out, we do have some debug queues that are available for the small runs, but with the default policy that you're only eligible to run on a maximum of 8 nodes. And so what about jobs that are larger than 8 nodes? So anything above 8 nodes, for example, a 16-node job, you would need to submit that to the default queue, competing against the rest of the projects. And also, the smallest allocable node count for a job is 128 nodes. And so even if you're only planning to use 16 nodes within the job for your runs, you'll be allocated 128 nodes in total. And so you need to wait for 128 nodes to become idle for your job to be allocated onto that. With all of this said, there are opportunities to sneak in short or large jobs ahead of maintenance windows. And so this is something that I find particularly useful when I'm debugging issues, even at the full machine scale. I love Monday maintenance days because I know that Sunday night into the early morning, Cobalt will be draining most of the machine, all of the machine, to put the maintenance reservation in place. And so that's an excellent opportunity to do some debugging runs, short runs or test runs. So in the past, especially on Mira, I've gotten a lot of half machine, full machine work done over the Sunday night. So I would encourage people to pay attention to these reservations as well for those reasons. Now, how to improve turnaround time within the debug queues. As Adrian mentioned, we have two of those debug queues, a cache quad and a flat quad. And my simple advice is, choose whichever queue has nodes readily available. If you're not impacted with for this small short job, if you're not impacted by performance or the memory bandwidth, really choose whichever queue has nodes available. So the default currently is in the default queue cache quad, but if you happen to get a flat quad node in the debug queue, I would point out that the default memory allocations are out of DDR, 192 gigabytes. And if the work that you're doing does depend on that memory bandwidth that's available, and your footprint is less than 16 gigabytes, then within the flat mode, you can use NUMA control to specifically allocate memory out of the HBM. And so this is an option for the app run command that's discussed in more details on the website. If your job can't quite fit within the debug queue limits, maybe you're running a 64 MPI ranks per node, and the issue you're coming across happens at 32 nodes. Well, if you have enough memory, if you can fit within memory, I should say, you can run a maximum of 256 MPI ranks per node to drop down within the 8-node limit. And if you're able to fit in memory and you can reproduce the issue, well, then you're able to debug the issue that you have within the queue limits for the debug queue. And so this can be something particularly helpful when debugging issues. This isn't something I would advocate for if you're doing a performance measurement. So trying to find nodes that are available to do this sort of quick turnaround work. The Grunculator is a good starting point, an estimate to kind of give a quick sense of what's going on. You can quickly see what's on the machine. Looking at the highest scored jobs, you can kind of get a sense of what will run next, what Cobalt will try to schedule next. And on the far right, in the red box, you can quickly get a sense of how many machines, how many nodes across the full machine are idle. This is helpful, in my mind, for some of the debugging work. This is helpful only if that number is above 500-600 nodes. And then this goes back to the reservations that might be in place. And also, if your work requires 128 nodes, are there 128 nodes in the default queue that are left idle? And so to really dig down into these details, you can make use of the nodelist command. So this is a very helpful command. It generates a lot of output. And so as I'll show you in the next couple of slides, you'll probably want to do some grepping and awking and sorting to clean up the output. Some of the important headers that are generated with this command are the queues that each node is allocable to, the status of that node. Is it busy running something? Is it idle waiting for work? Did it just finish up work and it's cleaning up and it will soon be available for a job to run on? And the last column is the backfill window. That node is idle, and any job that will run on that node within that backfill window could potentially run on that job. And the backfill window is Cobalt's estimate for when the next job it will schedule to run on those nodes. And so really what we want to look for is, if I need to run a job on n nodes, are there n nodes available with a backfill window larger than 30 minutes? And so if you can find a combination of nodes with that backfill window, that's an opportunity to quickly get something running on the system. And so here, there's a screenshot. I won't read through all of it, but you can look at the very top line, where my command prompt was, and the node list, followed by a number of Unix commands. And really, those are just trying to clean up and tease out information from all of the output. And so folks, depending on your particular needs, you would have your own combination of commands after that to process output from node list. And so here, when I'm doing a lot of this work, maybe I'm helping a user debug an issue, or I need a quick turnaround time on some performance run. I very routinely, I'm looking for free nodes. I want to do work quickly without waiting too long in the queue. And so with this particular instance, you can see that after running the node list command, there are 6 lines of output that are generated. I have boxes highlighting the 2 lines that are important for work, because in this example, this is something that won't fit in the debug queue. This is something that has to go into the default queue. And so I'm looking for how many nodes are idle that belong to the default queue that I could potentially run in. The very top line, it might be hard to see, but that one line has the CVD research queue allocated to those nodes. And so even though those nodes are idle, if I'm not part of that project or part of that the Unix group to get access to those queues, those idle nodes are not available for me to run on. So that's an important thing to be mindful of. And so in this example, I found that there were more than 500 nodes available in the default queue, and that the backfill window was about 46 minutes. And so for me, this is an excellent opportunity that I can quickly submit a 512 node job. In this example, I did it for 30 minutes, but if I really wanted to maximize the runtime, I probably would have said maybe 40 minutes for the window to allow that 6 minutes to give Cobalt time to process everything that's in the queue and get to my job and schedule it. So you really want to give Cobalt a couple of minutes lead time when trying to pack these jobs in with the short windows. And so all of this screen output is the one session. You know, I logged in, I saw what nodes were available. It happened to be more than 500, so I launched a 512 job for 30 minutes. A minute or two goes by, and my job was allocated onto the nodes. And so, boom, right then there, I can start getting work done on 512 nodes. I didn't have anything to do at the time. I was busy preparing slides for this, and so I exited and released those nodes back to the other users. And so this is just one example of, having to do something, you want quick turnaround time. How do you find what nodes are available? And a lot of this, if you're flexible in what you're doing and what you're working on, then you can get a lot of work done this way. A lot of the work that I do in these short jobs are interactive work, where I want to interactively work off the compute nodes, run multiple tests within a job script. And so appending the -I argument to qsub will submit the job not in batch mode, but in interactive mode. I also routinely, I didn't do it in this example, but I also routinely supply an email address with -m. And so most folks, they would probably insert their own email address. And so when your job launches, you'll get an email address, indicating that your job has started. So then you could, if you had context switched over to something else, you can quickly go back to your terminal and start working on your job. In some cases, you may be collaborating with somebody and you may be working together to debug an issue. So there is a possibility of adding multiple email addresses to this if you want. And so you and your colleague could both get an email that your job has started, and so now the two of you can maybe fire up a Blue Jeans session and start working together on something. Interactive jobs, just like all other jobs, they need to wait for nodes to be allocated and then for the job to start. And as we covered in the beginning, it's important to remember that the shell, when it opens up within your job, that you're no longer on the login node, you're not on the compute node, but you're on one of the service nodes, a mom node. In this particular example, the shell had opened up on the Theta Mom 1. And then again, as mentioned earlier, the app run command would be used to launch jobs on the compute nodes. One way of seeing this in practice is if you were on the mom node and you simply executed prac CPU info, you would see that you're sitting on a Xeon node, not one of the KNLs. But if you would then execute that command with app run, in this case a single rank, then that cat command will be executed on the compute node, and you can see that you're actually running on the Xeon Phi in that case. And so this can be important if you're trying to compile some application, being mindful of where you're at if you're expecting to be compiling on the compute node. And that's where the SSH attribute can be helpful, for example. This depends on the user and what the user's work is doing and how they're building the applications and so on. But the environment on the mom node may need to be refreshed in some cases. In my experience, I particularly see this with dynamic linking. In other cases, it may be that I just need to make sure that I have the modules loaded that I need for that particular work. And so if dynamic linking is the way that your application is being built, and you're on the mom node and you try to run the application and you hit errors that are of the flavor of error while loading shared libraries, a quick and easy thing to do, maybe just to simply export the LD library path given the value from the login node. And so in this example, you might have two shells open, one on the login, one on the mom node for your job, and you could simply copy and paste the LD library path variable from your login session to the job session. For more complex changes, maybe you have a specific set of modules that you need to load that maybe they're loaded in your script or maybe they're not. A handy thing that I also do for some cases is I save a copy of my modules that I have loaded from the login node into a default, my defaults, with the module save my defaults command. The action of that command will be to create a hidden directory in your home directory and a my defaults file that it basically lists a handful of environment variables that a module will replay to load up the environment. And so then with that file in place, every time I start up an interactive session, the first command I'd run is module restore my defaults. And issues like LD library path are fixed for me. LD library path may not be relevant for all workloads, but if you're routinely changing modules or you have your own modules and you want to load them, doing module restore can be a quick way to ensure that the session environment is what you need it to be. If you're doing work with Jupyter Hub, this allows you the ALCF instance. It allows you to work with the Python and Art notebooks, or you could open up a terminal within your browser, which can be handy for some folks. In this instance, you would log in with your ALCF credentials at the jupyterhub.alcf.anl.gov website. If you're working within a Python and an R notebook, you may be more likely to submit batch jobs in your notebook if you're doing that work, or maybe you're analyzing data. The interactive work where you want to be on the compute nodes, maybe you're more likely to do that within a terminal session. And so in this example, I fired up a terminal session within Jupyter Hub. I run the nodelist command. And so the find free nodes is just my nodelist command with all of the appendices for grepping in a little script that I use. So in this example, I'm looking for what nodes are available. I see a handful of nodes available in the debug queue. And so I quickly fire off an interactive debug job in the debug flat quad queue. And so I get onto those nodes and I can start doing some work right then and there. So again, if anyone takes anything away from these sites, I would say, use node lists and you can get a lot of power into your schedule.
Okay, so I guess I'll get started. I'll be talking a little bit about the case where you have a large number of potentially smaller jobs to run, or maybe a campaign of large jobs that dealing with the restrictions set by the scheduler, like the maximum number of queue jobs being 20, if those are too restrictive for you to get your work done effectively, you might want to consider a workflow. So before I go into that, I just want to motivate a little bit the case that Adrian started to talk about, which is a parallel ensemble job. So just as a quick reminder, your job scripts always start running on mom nodes, which are different architecture from the compute nodes. In your job script, your job script may have some hypothetical application that you want to run, and it launches instances of this application onto compute nodes with the apprun command. So by putting these into the background, we can do things like launch a first instance onto a single node, a subsequent instance onto two nodes, and then again like this. So you can see that we have multiple apprun processes running in the background on the mom node, and these all map to applications running on some number of compute nodes. Now this works great to pack a number of applications into your allocation up front, but what do you do then if you want to run more jobs? So suppose the green job finishes and then I want to launch another application. Well, if you do this without waiting, first of all, you'll get an error. So by oversubscribing resources, ALPS will complain that you don't have enough resources to run the application. So you may end up waiting on everything and then launching another batch of jobs once the initial backgrounded set has finished. But this quickly becomes complicated and it's difficult to maintain efficiency there. So oftentimes when you get into this scenario where you want to run parallel ensembles, but you also want to run jobs one after the other as they finish and efficiently utilize an allocation for some amount of time, you should consider using a workflow manager. So Balsam is one solution that is in production on Theta at Argonne. It's developed in-house in the data science group, and the main idea when you're using Balsam is that you own a private database of tasks and you submit unlimited runs of the applications that you want to carry out in your project to this database instead of directly to Cobalt. And then Balsam comes with some components like the service, which will then actually automate submission to the job queue on your behalf. And inside of these jobs, you have launchers, which are dynamically pulling jobs from the database and running them on available resources. So in this way, you don't have to deal with the details of which jobs run where and writing batch scripts to parallelize across resources. Instead, you're dealing with this database and a set of components built around it. And one of the advantages of going this way is that you have all of your provenance stored in the database. So the status of your workflow and any statistics about the recent runs, like throughput that you've achieved in the last week, are available sort of at a glance by interacting with a Python API to this database. So I won't go into too much depth on Balsam components in this talk, but I would like to point people at the documentation. So it's linked from the ALCF documentation, as well as here directly, you can go to balsam.readthedocs.io, and there are some tutorials for getting set up and running different kinds of workflows on Theta and other systems at Argonne. So just I'll give a quick demonstration of how you might start using it just to get your feet wet on Theta with a command line interface. So on Theta, there is a prepackaged module which has a Python virtual environment with Balsam installed and really all the necessary tools to just kind of create a database and start running immediately. So if you do module load Balsam, you get Python 3.6 and you get the necessary Postgres database in your environment. The command line interface has a single entry point of Balsam. So when you type Balsam, you get a help menu with the various possible commands that you can do. So the first one, when you're starting, is really you want to create a database that you start adding tasks to. So this you do with Balsam init. You pass a path to a project directory that you want Balsam to create. So this will initialize a database and some scratch area where your jobs will actually run. And you should get this success message at the end if everything is working as expected. Then you go ahead and use Balsam activate, which is sourced or with the leading dot, to actually set up some environment to let subsequent commands know that you're working in the context of this database that you just created. So when you use Balsam activate, it's kind of analogous to the conda activate commands where you set a particular project directory, and then this will start a database if one isn't already running for you, and set up the necessary environment variables. So in this case, we'd like to add an application just to test out the database we've created. We do this with the Balsam app command. And here I'm creating an application with a tag of say hello is the name. And the actual first part of the executable is just this bash built in echo hello. So we see a confirmation here that we've defined this app. And then we can create jobs that reference that application like this from the command line. So with Balsam job, we may create a job named test1, and we may want to group all of these test jobs under the workflow tests. So that's a way of grouping related jobs into directories that contain the, maybe all runs from the same experiment. And then you reference the application that we created here with this app argument, say hello, and then you provide the command line arguments to that application. So in this case, where we want to say hello world 1, and we do that by passing the string to the arguments there. And then we can run this in the second example. I just have a loop to create a few more of these jobs and kind of populate the database with a little example. And for each job that's created, what you should see is a little confirmation screen here. There are a large number of parameters that you can set on each job, controlling basically all aspects of its execution. So environment variables and all parameters that are passed through to AppRun if the job is using MPI, such as the number of ranks per node and so on. But what you probably want to pay attention to is the two summary lines at the bottom. So you'll see the executed command. In this case, it's that concatenation of hello and then the world 1 arguments. And you'll see the working directory, which is created here. So Balsam creates directories for each job on your behalf under your database. Finally, once you've done this and you've populated your database, you use Balsam ls to list the tasks in your database and kind of look at the status of your workflow at a glance. So in this case, you should see that you have 10 of these test jobs that are all created. And to actually start running something, you want to submit a job to the scheduler. And one of the easiest ways to do this is to use the Balsam submit launch command, which really mirrors the behavior of qsub. And what it does is it'll actually write a script on your behalf by filling out a template that you can actually hook into if necessary. And when this job is submitted, it will actually start the pilot job, which goes and pulls tasks from the database and runs them, and then updates the database kind of in real time. So in this case, I'm running a job on 2 nodes for 5 minutes on the debug cache quad queue, and I'm using this MPI job mode, which causes each application to be launched with an app run. So if everything works as expected, sometime later I do Balsam ls and I see that all of my jobs have finished here in the right-hand column. This is sort of the final state. And again, if I want to know where things have actually run, I can look under the data directory of my Balsam database. And so here I have a top-level workflow directory, which is named test because that's what I called my workflow. And then under each of these, I have a subdirectory for each of the jobs with the job name and an appended unique ID there, or a part of a unique ID. So that's just a quick, very quick look at basic command line usage of Balsam. There's also a Python API. So I would invite you to take a look at the documentation. And yeah, please let me know if you have any questions.
And again, I want to thank you all the presenters for their time and attendees to joining us today. If you have any questions or suggestions, please email us at alcfdevelopers@anl.gov, and we will be happy to hear your comments or suggestions about the next topic.